This is your video for section 3.3, and in this video we're going to start talking about the unit circle and circular functions. When we talk about the unit circle, that just means that we have a circle with a center at the origin and a radius of 1. The equation for this circle would be x squared plus y squared equals 1. Let's label some actual points on this circle. So if we're going 1 unit this direction from the origin, that would get us to the point 1, 0. If we're going from the center up 1 unit, that would get us to the point 0, 1. If we're going 1 unit to the left, that would get us to the point negative 1, 0. 1 unit down from the center would get us to the point 0, negative 1. What we're going to do is tie this back to our arc length formula. So if we're talking about S as an arc length, like we were in the last section, and we use this arc length formula, if we have a radius of 1, then if we put 1 into this formula, that tells us that S is actually equal to theta. So our angle is actually equal to our arc length. And what we're going to do is use this to find values of our 6 trig functions for S. What we're doing with this is that instead of thinking of the argument for our trig functions as being an angle, we're going to start thinking about it as being any real number. And that's why we're using S instead of theta. First, let's look at the sine of S. From what we set up here, S and theta are actually the same value. So the sine of S is the same as the sine of theta. And to find the same sine of theta, we can go back to our circle. Remember that when we defined our trig functions with the circle, sine was y over r. In this circle, our r is equal to 1. So that would give us y over 1, or just y. The sine of S is actually just equal to y. We can do the same thing for cosine. Cosine of S is going to be the same thing as the cosine of theta. In our circle definition for the trig functions, cosine was x over r. And since our r is 1 in this circle, that means that cosine of S is just equal to x. And then finally for the tangent of S, this would be the same as the tangent of theta. In our circle definition, tangent was y over x. So our tangent of S is just going to be y over x. Now this one, since we're talking about real numbers, this is only where x is not equal to 0. Now that we have those three, we can do the 3 reciprocal functions. So cosecant of S is going to be the reciprocal of this, which would be 1 over y. And that's only if y is not equal to 0. Secant is the reciprocal of cosine, so that would be 1 over x. That's when x is not equal to 0. And cotangent is the reciprocal of tangent, so that would be x over y, and that's when y is not equal to 0. This is how we can define our 6 trig functions as functions of just real numbers. We're not tied to thinking of them as just being angles. So those 6 definitions are written out for you down here. So we have that the sine of S is equal to y, the cosine of S is equal to x, tangent of S is equal to y over x, and then we have our 3 reciprocal functions down here. The reason that we use the unit circle for this is that it makes things so simple. So all we have to do to figure out the value of a function is know the point on the unit circle that that angle corresponds to, and all we have to do is say, okay, the cosine is x, so it's just the x coordinate of the point. The sine is just the y coordinate of the point. If we want to do the tangent, that's the y over the x. So this is tying everything to the points on the unit circle. Another thing that's nice about the unit circle is it's symmetric with respect to everything. So it's symmetric with respect to the x-axis, and it's symmetric with respect to the y-axis, and it's also symmetric with respect to the origin. And what that kind of symmetry means We talked about this in college algebra, if you remember that. If we've got a point AB on the unit circle, if it's symmetric with respect to the x-axis, that means that we would also have the point A negative B, which would be on the circle. If it's symmetric with respect to the y-axis, that means we'd also have the point negative AB. And if it's symmetric with respect to the origin, that would give us the point negative A, negative B. We can look at that with some of these specific points. So let's take this point. If we think of this as our A and our B, we've got the square root of 3 over 2 and 1/2. So if this is symmetric with respect to the x-axis, we should also have the point that's the square root of 3 negative 1/2. So that's this one down here. If this is symmetric with respect to the y-axis, then we should have a point flipped over the y-axis, and that's this point over here. So the x is the opposite, the y value is the same. And since it's symmetric to the origin, we should have a point that goes across the origin where both of these are the opposite value. And that's that point right there. And what this gives us is 4 different angles that are all in the same family, meaning that they have the same values for the points. In other words, for the cosine and the sine of the angle. It's just whether those values are positive or negative. So in the first quadrant, they're both going to be positive. So here's our angle in the first quadrant. In the second quadrant, the cosine or the x is going to be negative and the sine is positive. So there's that angle there. In the third quadrant, they're both going to be negative. And in the fourth quadrant, the cosine is positive, the sine is negative. Now that gives us 4 angles, and if you notice the radian measures of those angles, they're all in the same family, meaning that the denominator of each one is a 6. So we've got pi over 6 here. This one is 5 pi over 6. This one is 7 pi over 6. And this one is 11 pi over 6. So those 4 angles in the pi over 6 family all have the square root of 3 over 2 and 1/2 as the x and the y. Just in the different quadrants, those values might be positive or negative. Let's do the same thing for the angle pi over 3 and look at what happens to that family in the 4 different quadrants. So pi over 3 is in quadrant 1. For this one, we're just looking at the first quadrant angle, so we don't have a symmetry type, but the point where this angle crosses the unit circle, if we look at our unit circle up here, that point is 1/2 square root of 3 over 2. To find the cosine and the sine for pi over 3, the cosine is just the x-coordinate, the sine is just the y-coordinate. Then let's look at the angle pi minus pi over 3. If we go back to our unit circle, that would mean we're going all the way around here to pi, which is here, and we're backing up by pi over 3. That would get us back to 2 pi over 3. This is in quadrant 2. If we look at our first quadrant angle here, then the type of symmetry we're looking at is symmetry across the y-axis. And the point we have is negative 1/2 square root of 3 over 2. So the only thing that changed here is that the x-coordinate went from positive to negative. And that means our cosine is negative 1/2. Our sine is the square root of 3 over 2. If we look at the angle pi plus pi over 3, that means we're going around pi and then another pi over 3. That's going to get us to this next angle that's in the pi over 3 family, which is 4 pi over 3. And remember, if you're trying to figure these out, you can think of the fractions. So you can think of this as 1 pi plus 1/3 pi. And if you just add the 1 and the 1/3, that gives you 4/3. So that gives you 4 pi over 3. This is in quadrant 3. So the symmetry type that we're looking at is we're going all the way across the origin. And that means it's going to take both of our original values up here and make both of them negative. Then to find the cosine, we're just looking at the x-coordinate. That's negative 1/2. The sine is just the y-coordinate, so that's the negative square root of 3 over 2. And then last of all, if we look at 2 pi minus pi over 3, if we wrote this out as in fractions, that would be the same as 6 pi over 3 minus pi over 3, and that would give us 5 pi over 3. If we look at our circle, we're going all the way around to 2 pi and then backing up by pi over 3, and that gets us to right there. So that's in the fourth quadrant. The type of symmetry we have going from here down to here is going across the x-axis. What that means is that we're taking our point that we had up here and we're leaving the x value the same. We're making the y value negative. Our cosine is the x value, so that's going to be a positive 1/2. Sine is the y value, and that is negative square root of 3 over 2. Back in Unit 1, we talked about those Pythagorean identities. Since we're talking about the unit circle, this gives us another way to talk about that first Pythagorean identity. That is, if we take the equation for our unit circle, which was x squared plus y squared equals 1, we know that x is the same as the cosine of s, and y is the same as the sine of x. So we can replace the x and the y in here with cosine of s and sine of s. And then if we just rewrite this with the exponent in between, that gives us cosine squared of s plus sine squared of s equals 1. So this is back to that same Pythagorean identity that we talked about before. The reason that we're doing this is that now we can think of all of our trig functions as being just functions of real numbers. But when we think about functions of real numbers, we usually want to talk about the domain. If we're thinking about our inputs for these being real numbers, then for sine and cosine, we can put in any real number for the s. Our domain for this is all real numbers, or we could say it's negative infinity to infinity. These were the two functions where we said the x-coordinate of the point could not be equal to 0. And what that means, if we think about our circle, the places that the x is equal to 0 is going to be anything that's on the y-axis. Our angle values would be things like pi over 2, 3 pi over 2, so any odd multiple of pi over 2, 5 pi over 2, and so on, or negative pi over 2, negative 3 pi over 2, etc. So what we want to do is leave these values out of our domain. To say that in math terms, we could list it as intervals. We'd have a whole bunch of intervals. We'd just be leaving those values out. So we could have intervals like negative pi over 2 to pi over 2, and we would skip over the pi over 2 and start again, go on to 3 pi over 2, and we would skip the 3 pi over 2 and go up to the next one, and so on. So we have a whole bunch of intervals going in both directions. That would be one way to write the domain. Kind of a shorthand to write what we're doing here, which is we're taking all these odd multiples of pi over 2, is to put an n in there, say n has to be an integer, and to make it an odd integer in here, then we take 2n plus 1. So this is giving us odd multiples of pi over 2. For cotangent and cosecant, those were the ones where y can't be equal to 0. In terms of our angles, that means that we can't have 0, pi, 2 pi, or negative pi, negative 2 pi, and so on. So basically we can't have any multiples of pi. If we wrote that as intervals, then we would just be skipping over every multiple of pi. So we're skipping over negative pi, we're skipping over 0, we're skipping over pi, and so on. To write the shorthand for this, we use n to stand for an integer again, and this would give us any integer multiples of pi. So all of those values are left out of the domain.